Hi. Well, today we are going to start talking about chemical reactions. Maybe you thought we were talking about chemical reactions throughout this whole course, but really we had to take some time to learn about the structure of compounds. We had to learn about the periodic table. We had to learn about energy transfer. We had to learn about trends of the periodic table and of nonmetals and metals to really have that understanding before we get to chemical reactions. But now we are at that point, my favorite part of chemistry, which is chemical reactions. Now, unfortunately, we're not going to be in a lab such as this, but we're going to make do and make the best of the situation by being online and still make it a pretty good experience. So we're going to start by looking at the differences between chemical reactions and physical changes. So I hope you're excited. Here we go. All right, so doing a little review here. The difference between physical change and a chemical change. Physical change is when the chemical composition stays the same. So for example, if I have water is H2O, and if I freeze it, it still is H2O, it's just arranged differently. Those molecules are closer together and have less energy. Now if I add energy to ice and melt it, those H2O molecules are able to move further apart. If I add even more energy, then it becomes a gas. So I'm not changing the chemical composition. A chemical change, though, is when the chemical composition, when it does change and a new substance is formed, like wood burning or eating. Now, I don't want you to be confused seeing H2O as a product here and H2O as a product here. What's different is that I did not start with water. So here is a little example to show.
So as we add heat to water, the water molecules begin moving faster, and some of them spread out and form a gas. We call that gas water vapor, and that's what's inside the bubbles you see. These bubbles rise to the surface, and this is what we call boiling. So we'll start with the water molecule. The red is oxygen, and the two white atoms are hydrogen. That's H2O. Water molecules are always moving. When we add heat, they move faster. And if we add enough heat, they'll spread out and they'll form a gas. We call that gas water vapor. Note that there's nothing between the atoms here. The black is empty space. To understand why bubbles form during boiling, imagine a group of water molecules, and as you add heat, some of them spread out and form a gas, water vapor. When they spread out, they push the molecules around them away, and that forms the bubble that you see. That bubble rises to the surface. That's boiling. Remember, there are only water molecules in those bubbles. They're very energetic water molecules in the form of a gas, which we call water vapor.
Terms, combustion is the burning of something. Let's take a look at the combustion of wood. Wood is made up of a bunch of different compounds that contain mostly carbon, hydrogen, and oxygen atoms. And these compounds are held together by bonds. When wood is heated, usually from the heat of a match or a lighter, some of the bonds break, and as a result, different chemical compounds are released as vapor into the air. When these vapors mix under high heat with oxygen from the air, they burn and release more heat and also produce carbon dioxide and water. This is what sustains the flame of the fire. And if all that wood gets converted to carbon dioxide and water, it's called complete combustion. However, complete combustion of wood never happens. Combustion is not an instantaneous process. In addition to fuel, oxygen, and heat, combustion also takes time. So if any of these conditions are not met, then the vapors from the wood combine with the oxygen and nitrogen in the air, and they form other kinds of molecules and compounds, like carbon monoxide, nitrogen oxides, as well as unburned fuel and particulates or black carbon. These types of compounds are what make up smoke, which is bad for the environment and for human health.
So for the purpose of this unit, we are focusing on chemical changes. So looking at when the chemical composition changes and a new substance is formed. Wood burning and eating are just two examples, but there are thousands and thousands and thousands more examples. So then that leads us to, well, how do we know if a chemical reaction has occurred? Well, there's evidence that helps us to see if that happens. So when two or more substances are mixed, there might be signs like a gas forms. Now I know that in our last example, bubbles were forming when water was boiling. So that can't be our only evidence at times, but oftentimes when two species are mixed together, carbon dioxide gas can be produced, hydrogen gas produced, even water vapor can be produced. So these are all some examples. Another thing that's very common that can happen is that a solid can form. And if we look here, we have one substance being dropped by that eyedropper. We have another substance that's already in this beaker. And then we have a third yellow solid substance that's being formed by the addition of those two. So it's kind of, sometimes they're white, sometimes it's a white solid, sometimes it's different colors, but adding two different liquid species together and then to have a solid form, which is called a precipitate, is also an indication that a chemical reaction happened. Another example of a chemical reaction happening, or evidence to show it, is that there's a color change. And so we can see that a chemical reaction happened because I started with a pH of 4. I used litmus paper to detect that the pH changed to a pH of 10. So we can tell that by that color change that something happened. A lot of times people can use this to test their pool to see if the chemicals are correctly added. And we can use a pH meter if we're in the lab. And we can also tell by an energy change. And we can tell, obviously, by using a thermometer to tell if the temperature changed, if it got hotter, and sometimes you can just feel the heat. This has fire, so we can see that, but sometimes it's not as obvious as that, or sometimes it can get really cold and the temperature can plummet. So one important thing to remember when we are writing chemical equations is to write them correctly. And so we are going to look at how to symbolically describe the particulate and the macroscopic reaction. So we're pretty much just connecting the symbolic to the particulate to the macroscopic. And by doing that, we're going to use some common symbols. So obviously the elements from the periodic table. So if I said sodium added to water, so I would say Na was my sodium, but sodium what? This will help us if I would say I took solid sodium. So I would say it's Na parenthesis S. So this is going to be an important piece to remember when we're writing our chemical equations. So solid, liquid, and gas. And then our other state of matter that we're using is aqueous, aqueous. And that just means that if something is dissolved in water. All right, and then of course we have this NR, which shows no reaction, and then this triangle, which means heat, or change in heat. So essentially, if I see this triangle, that means that heat is added to the reaction. So the temperature is changing, but heat is being added to it. So let's look at this example. This is how it is read. I have a gas reactant or change in heat. So essentially, if I see this triangle, that means that heat is added to the reaction. So the temperature is changing, but heat is being added to it. So let's look at this example. This is how it is read. I have a gas reactant A. So whatever A is, what substance A is a gas. And it is mixed with another reactant, B. So I have two reactants, A and B. A is a gas and B is a liquid. So gas reactant A mixed with liquid reactant B. That's my left side of my arrow. And it yields, or it creates, or it produces product C, that's a solid, and aqueous D. So I have C and D that are produced. C is a solid, D is aqueous. And then we have our second example, number 2. And in this example, let's look at what it's telling us. Aqueous acetic acid. So here's my aqueous, and then acetic acid this is the equation for acetic acid. So aqueous acetic acid is added to, which is my plus, solid sodium bicarbonate. That's my solid indicating. This is my sodium bicarbonate. And then it tells me that it yields, which means arrow creates, produces aqueous sodium acetate, aqueous sodium acetate, and then there's a comma, liquid water, so and liquid water, L, liquid water, and, so that means another plus, and carbon dioxide gas. And we see CO2 in gas form. And then we can see below it is just depicting the same thing, but it's showing us the molecule. So we can see this acetic acid plus my sodium bicarbonate yields sodium acetate plus and water and carbon dioxide gas. So this shows me the particulate level. This is my symbolic, showing me the symbols, right? So then we see below that our pictorial kind of view of what we would see if we were doing this in the lab. So we have our solid sodium bicarbonate. I'm going to scroll back to our last slide here. Our solid sodium bicarbonate, and we added acetic acid to it. So we can see my solid sodium bicarbonate. That was my one reactant. And right here is my other reactant, my acetic acid. And then we can see the reaction happening. And here we see bubbles, which it showed us in our last one right here. Our bubbles, our gas is our CO2. And then inside the other parts of the reaction, we've got our liquid water, and we have our, what was our other one? Our sodium acetate that was created. So let's look at example 3 and example 4. So for example 3 and 4, I want you to try to fill in the missing piece, or what's missing from the example. So we can see here that here's what's happening pictorially. Here is the written symbolic equation. Here is the particulate level. So we are missing the, in words, what is happening with this reaction. And then this tells me that I have solid magnesium. And it tells me that this plus is here, and so that means it's added to oxygen gas. And then there's this arrow with the triangle on it, so that means heat was added to create solid magnesium oxide. All right, so we've got solid magnesium, that's the first one, is added to plus oxygen gas with heat to create, that's our arrow, solid magnesium oxide. There we go.
Now before you get started with example number 4, we need to recognize that with these ionic compounds that we're given that we need to write, we need to know those ions that they form. If we look at our periodic table, we can see that sodium is in our first column, so we know that sodium is a +1. And if we look at iodine, which forms iodide in a compound, we can see that it's in the halogens family, which is one before the noble gas, and it wants to be a -1 ion. Now silver is one of those special elements that is in the transition metals, and lots of transition metals have multiple different charges, and you would always be told what they are in parentheses. For example, if I said lead to oxide, that 2 that's in Roman numerals and parentheses tells me that my lead has a +2 charge. So you would be told that. Now silver is a special one where silver is always a +1 ion. So just make a note of that. And then nitrate we can find on our polyatomic ion sheet that you should have and is always going to be available. Nitrate is a -1 charge. So knowing that, and those charges, by the way, from reactants to products always stay the same. Knowing this information, I want you to try to write this chemical formula and write the whole reaction. So pause the video and then we'll come back and resume. All right, let's see how you did. Did you have that sodium iodide forms NaI? And that's because, again, sodium is a +1, iodine's a -1, and so just having one of each of those gives me a neutral compound, right? +1 and -1 is neutral. And it told that we were told that it was an aqueous solution, so we do AQ. And then it says that we are adding to that an aqueous solution of silver nitrate. So Ag is silver and NO3 is nitrate. Again, that's a +1 and a -1. It's already a neutral compound, and that's an aqueous solution. And then it says that they are mixed together to yield, so that's our arrow, a silver iodide precipitate. Okay, so silver iodide, that's +1, -1, and that's a solid precipitate. So we denote that with a S in an aqueous sodium nitrate solution. Sodium nitrate AQ. That's a +1 and a -1, so that's already balanced as is. Now notice that if I look on the left side of my problem here, I have 1 Na, and on the right side I have 1 Na. And if I look at the left side, I have 1 I and 1 I. And if I look, I have 1 Ag and 1 Ag. And lastly, I have 1 nitrate and 1 nitrate. So this is a balanced chemical equation, and we didn't even have to do any balancing. And in this next video, we are going to focus on balancing chemical equations.